Welcome to Chapter 2, Section 1, using inductive reasoning to make conjectures. Go ahead and start with a warm-up. To kick off inductive reasoning, let's just do this one out loud. You don't need to write this one down. So where you see the note that says orally, no need to write, you don't need to write that particular screen, but you do need to write the screens where you don't see that. So if we take a look at this pattern, find the next item in the pattern. January, March, May. What would you say is the next item in this pattern? January, February, March, April, May, June, July. You got it, July. So what we see here is a pattern that shows us alternating months of the year. And so the next month, the next alternating month, if we skip over June, would be July. Here's a number pattern. Go ahead and jot the number pattern down and see if you can name the next item in the pattern. 7, 14, 21, 28. You got it. These are multiples of 7, right? And so the next multiple of 7 is 35. Very good. Let's try a geometry shape. How about this triangle? So we see what appears to be a 45-degree right triangle or something like that. Maybe it's an equilateral. What happens between the first and the second and the third? What do you think will happen next? Okay, it looks like they're each making a 90-degree turn, doesn't it? 90-degree in a counterclockwise direction. If we look at this top vertex, it is now facing left, it is now facing down. Yep, you got it. So the next position would be to have that vertex facing right. Okay, the next item in this pattern, if you just take the numerals down, here we've got some decimal numbers, and you can see there's some kind of a relationship here. And think about it, and if you thought 4 is seemingly moving to the right by one place value, you got it right. So when we read the pattern from left to right, the next item in the pattern has one more 0 after the decimal point, or the 4 has moved one further place value to the right. So our next value would be 4 10,000ths, right? Very good. These examples you've been looking at and contemplating are inductive reasoning. When you are using a pattern to predict the next item in a list, you're using inductive reasoning. So assuming a pattern will continue, we're drawing a conclusion from a pattern. When we do that, the conclusion is our conjecture. So that's a statement that is true because a specific case we've seen, that statement is true for that case. Very good. So take these definitions down and we'll move on. So in this example, let's complete the conjecture. You don't need to write complete the conjecture. Just write the statement down. The sum of two positive numbers is... So go ahead and run a test. What happens when you add two positive numbers? Some possible tests would be 1 plus 1 equals 2, or 3.14 plus 1/100th equals 3 15/100ths. Or we can take a big pair of add-ins. We have 3,900 plus 1,017,017. And there is your 1,003,917. So what is the sum? What is common about these three sums? What's something basic about them? They are all positive. So the sum of two positive numbers is positive. That is the conjecture we can make, or that is how we can complete the conjecture, using the term positive. Okay, so let's try to complete the next conjecture. And so take this down. The number of lines formed by 4 points, no 3 of which are collinear, is... So to the right I have 4 points. So we can run a test here as well. If I grab a line, let me grab a line up here. Here's a line. And so let's see how many lines we can pass through any of these pairs of points. And we have, as you can see, 4 non-collinear points. No 3 points here could share the same line. So there's 1 line, here's 2 lines, here's 3, here's 4. Could we do another? Yeah, we could. We could do one here. 5. And look at that, we could make another one here. So you can see, it's kind of a pretty design. We have 6 lines that could be formed through 4 points where no 3 of those points are collinear. So we did this test. You don't need to take this information down, but you could draw a picture like we did here. And we did find that 6 lines could be formed through the 4 points. Complete the conjecture. The product of 2 odd numbers is, I'd like you to pause and go try experimenting with a couple of expressions where you have factors that are odd. What happens when we multiply 2 odd numbers? What is the product? And then pause and come on back. Okay, hopefully you have some good samples there, and hopefully you've seen something common about those products. So let's see what we have here. Some examples might be 2 odd numbers. 1 times 1 is 1. There we go. 3 times 3 is 9. And we can even mix it up and go with the next 2 odd numbers, odd whole numbers. We have 5 times 7, and 5 times 7 is 35. So what do these products have in common? 1, 9, and 35. And hopefully you recognize that they are all odd. Good. They're all odd. Let's try a real-world problem. You do not need to write this, but let's follow it through together. The cloud of water leaving a whale's blowhole when it exhales is called its blow. A biologist observed blue whale blows of 25 feet, 29 feet, 27 feet, and 24 feet. Another biologist recorded humpback whale blows of 8 feet, 7 feet, 8 feet, excuse my kids, and 9 feet. So we're making a conjecture based on the data. So what do we know? Right off the bat, what are you thinking? And hopefully you can right away see that the blue whale has a bigger spray than the humpback whales. Okay, so you can take this information that's been provided and we could put it into a table. And so that's been done for us here. So let's compare these. And so what is the most extreme height of any particular one of these pieces of data? And look at here, we can see this 29. So the height of the blue whale spray is 29. And let's see the height of the humpback whale. The highest is 9. Hey, Hannah. And so we see that definitely we could conjecture that a blue whale spray is higher than the humpback. Okay, so the smallest blue whale blow of 24 feet is 3 times higher than the greatest humpback whale blow of 9 feet. So the height of a blue whale's blow is about 3 times greater than a humpback whale's blow. Let's do another one of these conjectures based on data from the whale population. So this particular set of data is comparing the lengths of male and female whales. So this is interesting. Here's a table of information for average whale lengths. We have the length of females and we have the length of males. So take a moment to kind of observe. What do we see here? And what do you notice? So, interesting. We have mostly greater lengths in our females. Did you know that? Female whales tend to be longer on average than males. Notice here, this last piece of data, 48, is actually larger than 47. We have 48 here as well. So this female whale is on the shorter end, shorter side. But look at, there is no male whale that is in the 50-foot range here, so it's interesting. So in 5 of the pairs of numbers, the female is longer. So our conjecture is female whales are longer than male whales. So to sum it up, to show a conjecture is true or to show a conjecture is false, we experiment, don't we? We give examples, we find samples. So to show a conjecture is true, simply prove it with samples, examples. To show a conjecture is false, then give a counter example. So we need to make sure we can define counter example, and that would be an example that is shown to prove a conjecture false. Good. So we can put together a little rule box for inductive reasoning. So inductive reasoning is basically 3 steps. The first is look for a pattern. So when given a set of data, look for a pattern. And then make a conjecture. So what statement can you make when you discover the pattern? And finally, prove it or find a counterexample to disprove the statement. So let's have you write this conjecture down, and then we're going to prove that it's false. So you don't need to write the first sentence, but for every integer n to the third, n cubed, is positive. Is it possible that you could find a counterexample to this conjecture? Can you think of an integer that when you cube it is negative? And yeah, I'm sure you can, because we know that integers include whole numbers and their opposites. So if you plug a negative integer, let's just take -1 and plug it in. -1 times -1 times -1 is not positive. It is -1. So we would pick integers, substitute them in. You could use that -1 as an example. And they used -3 here. They let n be -3. Now remember, when you plug in -3 for n, it's as though the negative is in the parentheses with a 3. The entire thing is taking place 3 times, is a factor 3 times. So the conjecture is false. Okay, to save time, let's not write these next 2. Let's just walk through them and really try to come up with the answer before you hear it on the video. So let's show that this is false by finding a counterexample. 2 complementary angles are not congruent. So it may be possible that 2 complementary angles are not congruent, but is that always true? So what does it mean to have complementary angles? Yep, their sum is 90 degrees. So you could have something like 70 plus 20. 2 angles, 70 degrees plus 20 degrees is 90. They're not congruent. They're not the same measure. But could you have 2 angles that are the same measure whose total is 90? And I think you probably have it. And if you thought 45 degrees, you're right. So 45 plus 45 is 90, and those are congruent, and so the conjecture is false. Once again, let's walk through another conjecture and see if we can come up with a counterexample to prove it false. So for any real number x, x squared is greater than or equal to x. Okay, so recall what a real number is. These are all of our rational and irrational numbers. So rational numbers including fractions, integers, negatives, positives, whole numbers, 0, all of those. So when you start substituting values in, can you think of a number that when squared is actually less than itself, is what this is saying, right? Because this says that when you square the number, it's always greater than itself. So think for a moment and think rational numbers. So think fractional. So let's take, for example, 1/2. If I plug in 1/2, 1/2 squared is 1/2 times 1/2, which is 1/4. So is 1/4 greater than or equal to 1/2? No. So that's a great counterexample for this conjecture. It proves it false. So it's fractions that kind of are the special case here. So maybe this definition would be true for integers or for whole numbers, but not for all real numbers. So go for the lesson quiz, pause this, take it down, go for it, and go ahead and start your lesson.